In this exercise, we solve a system of finite difference equations to find a set of discrete points that form an approximate solution to a linear second-order boundary value problem. The boundary value problem is given by y double prime of x plus x times y prime of x plus y of x equals sin x, with the boundary conditions that y of 0 equals 0 and y of pi is equal to 0. The approximate solution will be made up of points x sub I, y sub I, on the interval from x equals 0 to x equals pi. The index I goes from 0 to the number of intervals which we designate as the whole number n. The partition points or nodes are 0, which we designate as x sub 0. X sub 0 is less than x sub 1, etc., 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 all the way to x sub n, which we set equal to pi. We defined y sub I to be equal to y of x sub I. We are going to use the software Mathematica for this exercise. To begin the Mathematica code, we define the parameters of the boundary value problem. If the standard form of the differential equation is y double prime of x plus p of x times y prime of x plus q of x times y of x equals f of x, then p of x must be equal to x. Q of x is 1. And f of x is sin x. We then define the endpoints of the interval. We set a equal to the left endpoint 0, and we attach a decimal point after 0 since we intend to use floating point calculations. We set b equal to pi. Then we define the number of subintervals. For the initial trial of the code, we set n equal to a modest 10 subintervals. We will also eventually try the code for n equals 50 subintervals, 100 subintervals, and 200 subintervals. We then set the subinterval length or step size h equal to b minus a divided by n, which is for a uniform partition. Then we define the boundary values. We will use the variable yy for the y values in the approximate solution, which will form an array, and to make the distinction with the variable y in the boundary value problem. Y sub 0 is 0. Y sub n, or y of pi, is 0. Then we define the x sub i's and their corresponding p, q, and f values. For this, we will use a do loop. Inside the do loop is a set of commands, so we use the curly brackets. The first command is to assign the x values. We use the variable xx instead of x since we are already using the variable x in defining p of x, q of x, and f of x. There are I step sizes from x equals a to xx sub I, and so xx sub I is a plus I times h. We use uppercase p for lowercase p of xx sub I, and so uppercase p sub I is lowercase p of xx sub I. Likewise, uppercase q sub I is lowercase q of xx sub I. And uppercase f sub I is lowercase f of xx sub I goes from 0 to n. We approximate y prime of x sub I by y sub I plus 1 minus y sub I minus 1 all over 2h, and y double prime of x sub I by y sub I plus 1 minus 2 times y sub I plus y sub I minus 1 all over h squared. These are central difference estimates for y prime and y double prime. From these central difference estimates, we get this equation for each I from 1 to n minus 1. We already have the values of y sub 0 and y sub n, so that the unknowns are y sub 1, y sub 2, etc., 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 all the way to y sub n minus 1. And so we have a system of n minus 1 linear equations in n minus 1 unknowns. In the code, we type equations for all the equations. For this, we use the table command. For each index I, the first term in the equation is the quantity 1 minus 0.5 times h times uppercase p sub I times y sub I minus 1. This is followed by plus the quantity minus 2 plus h squared times uppercase q sub I times y sub I. And the final term is plus the quantity 1 plus 0.5 times h times uppercase p sub I times y sub I plus 1. We have a double equals because this is an equation. On the right side is h squared times uppercase f sub I goes from 1 to n minus 1. We evaluate all the lines of code, and we have the system of equations on screen. To minimize on-screen clutter, we put this output in the background, so we type a semicolon after the equations command and evaluate again. We use the variable unknowns for the list of unknowns that we are going to solve for. We use the table command. The unknowns are the y sub i's, where I goes from 1 to n minus 1. We store the solution output in the variable s. We use the solve command. We are solving equations for the unknowns. We evaluate this last pair of commands, and we have the solution output on screen. We now form the points of the approximate solution by matching each x sub I to the corresponding y sub I. We label this set of points as points, and we use the table command. Inside the table command, we use the curly brackets, and inside the curly brackets are the coordinates x sub I and y sub I. Now, solving for the y sub i's does not automatically input each y sub I value into the variable y sub I. We still have to extract the y sub i's from S and input them into this table command, so that after the pair of coordinates, we type /period S double opening bracket 1 double closing bracket. I goes from 0 to n. And we put the solution output in the background by typing a semicolon at the end of the solve command to minimize clutter in future evaluations of the entire code. And now we plot the points by using the list plot command. To plot the approximate solution for n equals 10, we label the plot 10. In plot 10, we store the list plot of points. We will also color the points for n equals 10 as red, and so we use the plot style option with the RGB color directive. Inside the RGB color directive are 3 numbers, each between 0 and 1. If the points for n equals 10 are to be all red, we set 1 for R or red, 0 for G or green, and 0 for B or blue. And to ensure that we have the same region for the plots for the different values of n, we specify that the plot range lies between the y values of -1.3 and 0.1. This range of y values is something that we had predetermined when we tested the code before making this video. We execute this last pair of commands, and here is the approximate solution for n equals 10. Let's increase the value of n to 50, and to keep the plot for n equals 10, we change the variable name of plot 10 to plot 50. We will also make the points for n equals 50 all blue, so we have 0 for red, 0 for green, and the maximum 1 for blue. Before we evaluate anything, we must go back to the start of the code and change n to 50. We should also point out that for n equals 10, y sub 10 is y of pi, which is 0, so that y sub 10 is currently not a variable. But for n equals 50, y sub 10 is supposed to be one of the unknowns, so that when we resolve the system, y sub 10 as a variable will run into conflict with the pre-assigned value of 0 from n equals 10. So we must clear all definitions of xx and yy just before the definition of the boundary values in the code. We clear xx and yy. We then evaluate all the commands. To view the plots for n equals 10 and for n equals 50, we use the show command. We show plot 50 and plot 10. We evaluate this show command line to view the plots. Some of the red dots, which are for n equals 10, seem like outliers, which might be due to the fact that n equals 10 uses a coarser partition of the interval than n equals 50. Now let's increase the number of subintervals, this time to 100. We rename the plot Plot 100. We'll also change the RGB color setting to 0.8, 0.3, and 0, so there's some red, a little bit of green, and no blue. We insert Plot 100 in the show command. We go back to the beginning to change n to 100, and evaluate all the lines of code. Here is the combined plot for n equals 10, n equals 50, and n equals 100, with the points for n equals 100, which are the brownish dots, filling in more of the gaps between the points for n equals 50. For the final value of n, we change n to 200 and name the plot Plot 200. We change the RGB color setting to 0 for red, 0.7 for green, and 0 for blue. We insert Plot 200 in the show command. We go back to the beginning and change n to 200, and evaluate all the lines of code. As more and more points are added to the graph from n equals 50 to n equals 100 to n equals 200, some of the red points, which are for n equals 10, seem more and more like outliers. It also seems, as a matter of speculation, that the points for n equals 50, 100, and 200 lie close, if not on, the solution to the boundary value problem.